Okay, so we're gonna not go through these notes. We'll do that on Monday, but I'm gonna jump all the way pretty much to the end. So here we go. Catch up. Okay, here we are at Poiseuille's equation. And I just love this equation. It's so beautiful. So we have the flow rate here, volume for time. So this is flow through a tube. And this is the big deal. It's radius to the fourth power. Wow. Okay. If the viscosity of the fluid is big, it's not going to flow as fast. All right. So velocity is that drag on the flow. If I double the velocity of viscosity, I'm going to cut the flow in half. So you can just look at this equation and see viscosity in the denominator to the first power, right? And so if I double that viscosity, I put a 2 down here in the denominator, I've cut the flow in half. Okay. This is x2 minus x1. This is essentially the length of the pipe. And then this is the pressure difference at the beginning and end of the pipe. Okay. So this would be I'll call it insertion pressure. I'm trying to figure out what I want to call this. And this is the exit pressure. I mean, that makes sense too, right? If you're flowing through a pipe and you pull a vacuum on the end, you're going to get a faster flow. Okay, you're dropping that P1, you're going to have a bigger numerator, the flow is going to increase. Okay, but there's a limit to that. You know, a perfect vacuum compared to atmospheric pressure is only a difference of 14 pounds per square inch. If you were to convert that to millimeters of mercury, how much is it? You guys know this, right? So atmospheric pressure, if you pull a vacuum on this side of a loop of mercury, a perfect vacuum, and you have atmospheric pressure on the other side, what's the difference in height of the mercury? It's going to come around to the vacuum side, but it's going to stop eventually. What's the unit of millimeters of mercury? No. Freshman Chem 1. Pressure, unit of pressure. 760. Yeah, 760 millimeters of mercury. So that's almost a meter, right? 1,000 millimeters of mercury would be a meter. Okay, 760 for mercury. Now we use mercury for two reasons. It's liquid, so we can do this tube thing where it flows, and it's really heavy. It's really dense. So 760 millimeters of mercury is 14 pounds per square inch. If I put a column of mercury on a square inch, 760 millimeters tall, that'd be 14 pounds. Now, how much water would it take to get 14 pounds? It'd be like
water. 14. Water's heavy.
Yeah, but not as heavy as mercury.
It's
Yeah,
be a lot taller.
lot taller. Be like 37 feet.
Several millimeters.
Yeah, and so you can't. The only thing pushing that water or that mercury up the straw, right, is atmospheric pressure. And you have perfect vacuum at the top, and mercury is only going to go up 760 millimeters, even with a perfect vacuum on top. Water would only go up 36 feet, 37 feet. I think it's 36 feet. With a perfect vacuum on top and atmospheric pressure pushing on the other side of the straw. So what that tells you is there's no way you could suck a liquid through a 37-foot straw. Even if you pulled a perfect vacuum on it, the only thing pushing it up is the atmosphere. Okay, and so it's kind of like this flow. The exit pressure, right, is the best vacuum you could get. Okay, and this length, atmospheric pressure, that difference is only going to get, basically flow is going to stop in that situation. Now, if you give it a larger insertion pressure, then you can have a flow again. Okay, so these two pressures are interesting to play around with. But this radius to the fourth power. I play around with that a lot in the homework. And then I have some questions about viscosity. Maybe I have them for length of the pipe. I'm not sure. And so, so this is the equation I'm intending you to use for that homework that's due on Saturday. And then we'll talk about viscosity and what's going on with that on Monday. But then we'll probably finish about halfway through Monday, and then we can do questions on the homework and stuff to prepare for Wednesday. Sound good? Okay. All right, good. Now, our viscosity lab is next week. We're not using an Ostwald viscometer. We're using a falling ball viscometer. So the little ball will fall, and you time it between 2 marks. And I have like an extra, it's not extra credit, it's just like a different way to collect the data. And that is, if you have a video software that can get frame by frame, if you video it, then you get more accurate times, right? But if I require students to do that, sometimes they can't find a software package that will tell them the frame, like times. They'll tell them what frame they're on, but not the times. So they can't do the time difference. But if you have access to video software, you can collect your data that way, where you turn it, your partner turns it up, the ball goes to the top, you flip it over, the ball starts to fall. If you video that, you can find the frame when it's between the 2 marks at the top and the frame when it's between the 2 marks at the bottom, and then you can get the difference to accuracy of like a 30th of a second, and then you can get really accurate times. Otherwise, you're using a stopwatch, and you're like, okay, go, okay, stop, and it'll work. You got to do it 5 times, right, so that you get good statistics. Okay, so that's Monday's lab. We're measuring viscosity of water and then the various surfactants that your teams used. So you'll use the same surfactant you used for the surface tension, and you'll get the viscosity. Okay. So that's next week. And then we have 1 lab to go, but we're going to delay a couple of weeks so that we can do the radiochemistry stuff, and you can understand what radioactivity is before you go in and actually measure it. So that'll be fun. Y'all have a good weekend.